Hello, ladies and gentlemen, and welcome back to more of the 2002 Euclid contest. We're on question number 4. We're moving right along. Question 4 has two parts, the first one of which has a light, but it does have two parts, right? Yeah, two parts. Although part B appears to be split up into 3 smaller parts, so maybe we might say this has 4 parts. Alright. But part A is a light bulb. That just means final answer is needed. In the diagram, triangle ABC is right angled at B, just as they have shown. MT is the perpendicular bisector of BC. So we have to recall what a perpendicular bisector means. It means that it hits BC, the side that it's bisecting. It splits it in half, so BM is equal to MC. And it also hits it at a perpendicular or right angle. So M's on BC and T is on AC. If AT is equal to AB, what is the size of angle ACB? Alright. Well, let's just redraw this picture in our notebook, and we can fiddle around with it, see what we can see. Right angle. We have a perpendicular bisector right here. M, B, C, T, A, and we're just going to immediately highlight in green. We want this angle, right? Let's double check. Yeah. ACB, we want the tiny little angle way at the end. Okay. So, let's label some things. If it's a perpendicular bisector, that means it splits, now let's get some colors in here. Splits this fella in half. And we're also told, our assumption is that AB is equal to AT. Let's just use a single dash here. Okay. So the first thing I'm noticing is, right angles here and a common angle at C. We must have similar triangles. So I make sure triangle ABC is the same as, keep the order right, TMC. They're similar, not congruent, just similar. Okay. Well, if they're similar, then that means their side lengths have a common ratio. Doubling, tripling, so there's some ratio R. So that, let's see, AB is equal to R times TM. BC is R times MC, the corresponding side, and AC is R times TC. There's some R, and it solves all these equations, and in particular, it solves this one right here. So since M is the midpoint, because remember TM is a perpendicular bisector, so it splits it in half. The midpoint of BC. You see that BC is going to be 2MC. That tells me that my common side length, or my common ratio for the side lengths is 2. Okay. So, what can I do with that? Well, AT, let's see, AC, I can split that up as AT plus TC. But then, AC is also 2 times TC, and that's TC plus TC. And if I comparing these two equations, we see that AT is going to be TC. But AB is AT. We're told that as well. So, oops, wrong button. Wrong button indeed. That tells me that they got a purple dash there. So we have a right angle triangle. We've got a 1 to 2. Looks like we're looking at a 30, 60, 90 triangle. This makes me think of a 30, 60, 90 triangle. So 1, 2, and we get a root 3 over here. This is a very special triangle because we have interior angles of 30 degrees, 60 degrees, and 90 degrees. It's a very common type of triangle. It comes up a lot on math contests. And that tells me that angle ACB must be 30 degrees. Another way we could have said that is using SOHCAHTOA. If you didn't want to just invoke the power of the 30, 60, 90 triangle, you could have said SOHCAHTOA. That means that sine of angle ACB is going to be AB, the opposite, over the hypotenuse, and that's just going to give you a ratio of 1/2. And so sine 30 degrees is the only one that has 1/2, and that tells you the angle's 30 degrees. There's two ways you could have done it. It doesn't really matter. It's a light bulb question, so all you really need is the final answer. It's important to show your work, though, to get part marks, as I always say on these contests. All the written contests, important to show part marks, even if they're just asking for a final answer. Show your work. Okay, so that was A. Now we've got B, which is a graph. What's going on here? So the graph of y equals f of x, we're not even told what f of x is. Oh, no, there it is. F of x is 2x. Geez, I really should read a full sentence before I start talking. So the graph of y equals f of x, or let's just say y equals 2x, is given on the grid below. Pretty nice graph there. And then we got three little sub-questions on the grid in the answer booklet. So obviously this year they had a grid in the answer booklet. We don't, but we'll make do with a grid that we'll draw. So on the grid in the answer booklet, draw and label the graphs of the inverse function, y is equal to f inverse of x, and the reciprocal function, y equals 1 over f of x. Okay. And then we need to state the coordinates where these two guys are equal. And we also need to determine the numerical value of f inverse applied to 1 over f of 1/2. Okay. Well, it might be nice to work out functions for these two. So y equals 1 over f of x, that's just going to be 1 over 2x. That's not particularly interesting, although we'll still graph it. But f inverse of x, we could probably actually work out what that'll be. I think it'll be a 1/2 x. Okay. So, how are we going to do this? Well, there's a couple ways we can do it, I think. Let's draw a nice bit of graph. So, they go up by 2s, I think. We're going to go up by 1s just so we can be super accurate. That's 1, 2, 3, 4, 5, 6. 1, 2, 3. I suppose I could use the... No, let's clear this. I suppose I can actually... I use grid paper anyway in the background. Let's actually use the grid as much as we can. So every 3 will be 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. -1, -2, -3, -4, -5. 1, 2, -3, -4, -5. Okay, that's as far as we're going. So, I'm going to actually draw our original function as well on here, so that I won't need to keep flipping back. It's 2x, so that means its x-intercept is just going to be 0. And then, got a point here, we've got a point here, and another point here, and another point here. So there's y equals 2x. Okay. So, one thing we could do, if we wanted to get any of these, really, we could make a table of values. So, for example, if I want 1 over 2 of x, if I want to graph that, one of the safest things we can do is just plot points and then draw a nice smooth curve in between them. So what do we have? We got -5 over here, so I'd start with -5, and then I'd do -4. And I'd just work out what each of these is. 1 over -5 times 2, so that's -1/10. This will be -1/8. And it'll just keep going, and I would graph each of these. So I would plot -1/10 down here, and then -1/8 down here, and keep going. Another thing we can do is we can, so we'll do that for this one. Now when it comes to doing inverses, there's a much nicer, cleaner thing we can do. So 1 over -4, that's -1/4. Then we're going to have -1 over 2. So we're not going to have anything here. It's actually going to be a vertical asymptote. It's going to skyrocket downward, I guess. We'll deal with that in a moment. And then we'll have 1/2, 1/4, 1/6, 1/8, and 1/10. When I look at this function, it reminds me of the graph of 1 over x, and that looks like this. Now we're going to have 1/10, 1/8 is a little better than 1/6. All of these are too far out. There we go. So now those aren't getting in the way. So 1/10, 1/8, 1/6, 1/4, 1/2, and then 1/2, 1/4, 1/6, 1/8, 1/10. We'd have 1/12 here if we kept going, but I'm actually going to stop. That way we have 5 on each side. I don't know what the graph paper they gave you looked like for that year. And then in a nice blue, we're going to draw this guy. And he's going to come down like this. Okay. So that gives us 1 over. So the blue one is y equals 1 over f of x. And now in orange, I guess we'll do the inverse. So one of the nice things we can do with an inverse is if we have the graph of the original, and we plot the graph y equals x, then all you have to do is sort of reflect the points here. I don't want to do it this way. And I'll tell you why. I don't want to do it this way, even though it's perfectly valid. It's because it's just very hard to do the reflection. But it's a perfectly nice way to do it if you can pull it off. Instead, what I'm going to do is I don't want to quite do a table of values again. But I could, anytime I have a coordinate, so let's say I have 2, 4, that means if I flip these two, if I rearrange the x and y coordinate, that's going to give me a coordinate on the inverse. Alright, so that's something we can do. So this point means that I'm going to have a point here at 4, 2. And what I can do is I can ask, okay, that's where it was with a height of 4. Where was it with a height of 5? Well, it's at 2.5. So at 5 here, we're going to have a point that's 2.5. And however you did it is fine. If you did them both with table of values, I salute you. Those are perfectly valid ways of doing it. And we can get points here all the time. Anytime we have coordinates here, just flip them and you'll rearrange them and you'll get coordinates on the other one. We get 1/2. Actually, it's the same point on both of them. That probably helps to answer the next one. But once we have enough points, we realize, oh, this is going to be a line. In fact, it's going to be the line y equals 1/2 x. If you were able to realize that from the start, bravo. And we just keep going. Table of values would have worked fine as well. Our reflection technique would have been fine as well. I just wanted to sort of emphasize where the coordinates are going, I guess. And again, I don't know how big their graph was, but I have to imagine it was probably comparable to this. Okay, so that's 2 ways we can do it. And that was sort of B1. B2, what have we got? State the coordinates of the points where this is equal to this. Okay. Well, as I already remarked, F inverse, because we got to show our work. F inverse is just 1/2 x. And this is 1 over 2x. Okay? So we rearrange these, multiply both sides by 2, I guess would be the best thing. We'd get x is equal to 1 over x. And then multiply both sides by x. I guess we get x squared is equal to 1. So x is going to be plus or minus 1. That tells us the x coordinate, but we want both. We want the x and the y. So when x is equal to 1, 1/2 x gives us 1/2. And when x is negative 1, then we still have y is 1/2 x. Substitute your x value into either one of the equations. They're both supposed to come out the same way. That's a good way of checking. And we get 1/2 and negative 1/2. So that 1 and 1/2, and -1, -1/2. And if we go back, our graph actually reflects that. And if at this point, I would go back and make sure, does my graph reflect that intersection? Because I should definitely make sure it does. Because otherwise, that might be something they're looking for in the marking room. Okay? So state the coordinates of the points where that happens. We've got them. We worked them all out. There were 2. Now, determine the numerical value of f inverse 1 over f of 1/2. Okay. Well, what's f of 1/2? That's 2 times 1/2. So that's f inverse of 1 over 1, which is just f inverse of 1. And f inverse is 1/2 x, so this is 1/2, so we get 1/2. Okay. We'll have a final little therefore statement, I guess. Very nice. And that rounds it all up. That's the last part. You got the numerical value there. And that finishes off question number 4. In the next video, we're going to take a look at question number 5 on this Euclid paper. Thank you guys for joining me. And as always, I'll see you for more math fun in the next video.